like to print out a little cheat sheet. I can never remember actually what I'm going to say, and sort of pin it up somewhere so I can see it. But it's printed out in such microscopic type that I'm not going to be able to fool anyone today. Set my watch. Okay. Right. This is a talk about joint work with Bob Cooker, my supervisor here at Oxford, and Rob Speckle. Where's Rob Speckle now? Yeah. Okay, so what's the talk about? Okay, I'll start with a few questions. What's sort of special about quantum mechanics? What are the really inherently quantum features about quantum mechanics? Is it incompatible observables, no cloning, the possibility to do certain protocols, violation of Bell inequalities? What are the sort of mathematical origins of these features? And to what extent are they independent or interdependent? Can we take out one and still have others, or how does that all work? And I guess in an effort to answer questions like this, in recent years people have proposed sort of quantum-like theories that have similar features with quantum mechanics, but don't share all of the same features. And I suppose examples of this that I think of, I guess, would be super non-local quantum theories, not quantum theories, super non-local theories, or the one that I'm going to speak about today, which is a toy theory of quantum mechanics, which was developed by Rob Speckle, which achieved quite a lot of attention. Now, all these theories look quite different mathematically. They use quite different structures, and what we're going to sort of talk about today is trying to find a common framework in which to view these theories, so that we can maybe sort of spot what similarities they have that might be masked by their different sort of formulation, and also be able to pinpoint differences more clearly. And what we also might hope is that if we can spot mathematical differences, that these might correspond nicely and directly to differences in the phenomena that these theories exhibit. Okay, so I'm going to concentrate on comparing two theories today as a sort of test of this. Rub that out. One is a restricted version of quantum mechanics, which we'll call stabilizer theory, and the other is this toy theory by Speckle. And we're going to try and, using this unifying framework, identify some structure which both these theories have in common, and also identify a sort of subtle difference in this structure. And furthermore, this is going to be related to the main sort of physical difference between these theories, which is that this is essentially quantum, and this is a local hidden variable theory. So this sort of lacks the non-locality of quantum theory. Right, so what is this framework I'm going to use? Slightly unoriginally here in this conference, it's actually going to be this symmetric monoidal categories framework, which we've heard quite a lot about already. I think we've already heard plenty about it, in fact, so I'm going to skim very quickly over the basic idea that I think we've already heard what a category is. In many sort of physical theories can be sort of viewed as instances of a symmetric monoidal category, where our systems are the objects of the category, processes that they undergo are the morphisms of the category. Other sort of key features, I'm not sure if anyone has talked about this yet, that we have a nice graphical language for representing morphisms within a symmetric monoidal category. So if this is a morphism F going from A to B, I'm going to represent that as a box F with lines coming in A and line going out B. And here are sort of how I would compose these systems via composition and via the symmetric monoidal structure. should just add quickly that this sort of morphism here, we're going to interpret as the preparation of a system A in some state psi. And I will use this graphical representation over the course of the talk. Okay, so these two theories, I should say a little bit more about them. First of all, the stabilizer theory. This is like a restricted version of quantum mechanics in which we're only going to consider, the only systems we're going to consider are qubits, although we can consider sort of larger composite systems of multiple qubits. And the only states we're going to consider are the stabilizer states. Now, sort of technically, the stabilizer states are eigenstates of tensor products of Pauli operators, but that doesn't really matter too much here. The important thing is that they're a discrete set of states. They're not continuous, if you like the states of full quantum theory. In the case of a single qubit, we've got 6 states here. These are the eigenstates of the 3 Pauli matrices. When we go up to a larger number of qubits, we get sort of tensor products of these states and also entangled states like Bell states and so on. And the morphisms of this category are the morphisms which preserve the stabilizer states. So, for example, our unitaries are the Clifford unitaries, and the unitaries acting on the single qubit states are the single qubit unitaries, which form a group S4, the permutation group. Okay, I should talk briefly about the other theory. This is Speckle's estoy theory. I could say, quite a lot about this, but I saw what happened to the other speakers. So, yes.
You cannot take a complex combination of the states.
Yes, I know.
You can?
No, you can't. Yeah. Okay. The Speckle's estoy theory. Once again, there's only a single type of system in this theory, and it's in some sense meant to sort of resemble a qubit. Now, this single system has basically 4 states it can be in, and these are, Speckle calls these the ontic states. And here's the sort of the state space of the system, so we can either be in one of these 4 states. However, part of the theory is to postulate that there's some sort of fundamental restriction on our knowledge of the ontic states, such that, simplifying a little bit, the best we can do is sort of to know that the system is in one of 2 different states. So, our state of knowledge, which Speckle refers to as the epistemic state, that's sort of the analogue of the quantum state. And so, for example, we've got sort of 6 possibilities for a single system here. And I've drawn them kind of suggestively on the block sphere because if you work through the details of the theory, then you start to reproduce a lot of the features of quantum mechanics, and these can be seen sort of analogously to the 6 stabilizer states which I talked about a second ago. And you can sort of use this restriction on knowledge to work up and figure out what sort of transformations are allowed in the theory. On the single system, it's permutations of the ontic states, which again form the group S4. And you can figure out what the states on sort of composite systems are. I won't go into the details of that. Now, what we want to do is try and incorporate both of these theories into our overall categorical structure. Basically, we've got, we want to define 2 categories, which we will call stab and spec. And, okay, now we talked earlier about how the category F-Hill in some sense embodies the theory of quantum mechanics, full quantum mechanics. And so, unsurprisingly, since stabilizer theory is a restricted version of quantum mechanics, this is going to be a symmetric monoid, a dagger symmetric monoidal category of F-Hill. Interestingly, we can sort of define stab in a kind of a constructive way. We say that these are our objects here. We've got the sort of trivial monoidal identity object, and the state space of a qubit, and arbitrary tensor products of that. And the morphisms are category are the closure under composition, tensor product, and adjoint of the following operations: the single qubit Clifford operations, and this operation here, this operation which copies a particular basis, and finally this operation here, which sort of maps into the plus state. The reason for the terminology will become clear later. And I don't really have time to prove why that will give us all the stabilizer states and operations. You take my word for it. Again, you'll have to take my word for it that this construction gives us all the states and processes of the estoy theory. It's quite a similar sort of process. In this case, we have a sub-category of the category rel, whose objects are sets and whose morphisms are relations. And in this case, our objects are the single element set, the 4-element set, and sort of arbitrary Cartesian products of this. The morphisms are the closure under composition, Cartesian product this time, and relational converse of all the permutations of this rather odd relation here, and another relation here, which aren't probably particularly enlightening, especially not if you're not familiar with Speckle's theory. If you are, then you might be able to see something of what's going on here. Okay. Okay. I have defined these in a sort of analogous way, but despite that, it's still not really obvious that these categories have got that much in common. I mean, one involves vectors, linear maps, the other involves sets, relations. What I want to do now is pick out some structure which both theories, both categories share, which isn't immediately obvious. So to that end, to begin with, I want to define what I'm going to call an observable structure. You can see we sort of struggled with the terminology on this one, and I've gone back and forth a few times. At the moment, we're calling it an observable structure. Basically, an observable structure is an object X and two morphisms, delta and epsilon, represented graphically like this, satisfying the following 5 relations. There's 3 of them here, done graphically, and another couple here. Okay. We sort of justify our terminology of observable. Yeah, then I have to put on other stuff that I don't want you to see, which is recycled. Okay. We didn't write all of these for this talk. We justify this terminology, observable structure, because in the case of F Hill, and in fact in STAB, these observable structures are in one-to-one or bijective correspondence with orthonormal bases. And how exactly, I mean, the sort of explicit details of how that works, I'll go back to the definition of the category. You're talking about things like this being our delta and I epsilon, and we pick out a particular basis by the fact that this delta copies that basis. I should also add as well that these two here in spec also form an observable structure. Okay. I want to just very briefly give a few more definitions. We want the sort of abstract counterpart of these states that would be in these orthonormal states which are being copied by the basis structure, the observable structure. There we go, more terminology change. Basically, an eigenstate of a observable structure is a state where we get where this law holds. I also want to give a sort of abstract counterpart to unbiased state. A state here is unbiased with respect to a particular observable structure if this object here is unitary. That is to say, if we take the dagger of this operation here, we get the inverse of this. Now, that isn't particularly obvious why that makes this state unbiased, but we again sort of justify that by saying that in the case of F Hill and in stab, we get exactly those states which are unbiased with respect to the eigenstates of this observable. And finally, at the bottom, two observable structures are mutually unbiased if all the eigenstates of one are unbiased with respect to the other. Okay. Right. Okay. Now I want to take this delta morphism, which we talked about in the observable structure, and flip it around using the dagger operation. And I get now morphism from x tends to x, or x, whatever, x to x. And if I apply this to two states of x, that is morphisms of type I to x, then I get out another thing of the same type, essentially, another state. And if we go back to the defining properties of the observable structure, all those diagrams, get on nice and organised, all that stuff, then it's not too hard to verify that this operation here, this delta dagger, forms a sort of a monoidal multiplication on the states of x. In fact, the unit is this thing epsilon dagger, which was also appeared as part of the definition of the observable structure. Now, if we restrict to the states which are unbiased with respect to this basis, this observable structure here, then they form a sort of a subgroup of the monoid. They're all inverses of one another, and we get something which is going to be important for the rest of the talk, something we call the phase group. So that's the subgroup of this monoid, where we just consider the unbiased states. That's an abelian group because this is a commutative monoid on account of these properties of the observable structure. We call it the phase group again. Why do we do that again? Because in the case of full quantum mechanics, F Hill, for the basis structure which copies these two, if we're looking at the block sphere here, these are all these sort of phases around the equator are all the unbiased states. Okay. Right. How am I doing? Okay. So, just very quickly, we sort of, if we've got, in the case of stabilizer theory, if this is if we've got the observable structure which copies these two states, or these two are the eigenstates, then we have four unbiased states here. So these are going to form the phase group here. And in the case, again, of Speckle's theory, suppose we have the delta, which I used in the definition of the category spec. That turns out to have these two as eigenstates, and these four around the middle as the unbiased states. Okay. Last bit of definition. We're going to define something that's sort of the abstract equivalent of the GHZ state. I'm going to define it in terms of this observable structure, which we've already talked about. So, a GHZ structure, that's an object x and a morphism here from I to x cross x cross x. So it's a sort of a tripartite state, and we define it in terms of the observable structure like that. In the case of F Hill and in stab, we get exactly the GHZ states which we're used to. And this object here has various sort of properties symmetry properties, for example, which we would like in the sort of abstract counterpart of the GHZ state. Really last bit of definition are what I'm going to call correlation triples. So, suppose we have, where are we? This is our GHZ structure on this object X, and we have states X, X prime, X double prime, all states on X. Then a correlation triple is a triple of states such that this property holds here. Now, to try and give you an idea of what that really means, or how we interpret that, essentially, if we were going to sort of cap off this diagram here with another state here, then this would, sort of glossing over a few technicalities, be sort of like the probability of if we made measurements on each of the parts of each of the components of the state, that we got these particular outcomes labelled by these states. So, for example, suppose we tried to measure this. Suppose X double prime is the eigenstate of some observable, and we take another eigenstate of that observable, and we consider the triple X, X prime, and this other eigenstate. Then, basically, this scalar here, when we cap this off, is going to be 0, and we have no possibility of ever achieving that combination of measurements together. So what these correlation triples give us is sort of, they spell out forbidden triples, which can never occur in any measurement. Finally, the key point is that this phase group, which I just talked about, or the monoid, sorry, which I just talked about, is quite closely related to these correlation triples, in that correlation triples are always of this form. And that's not so hard to believe, given that we've defined the GHZ structure in terms of the observable structure. Okay. Okay, just coming back very quickly to our definition of stab and spec. Now with a bit more knowledge, with all these tedious definitions. In the categorical approach, we're not really that interested in sort of what the objects and morphisms are, how they're sort of defined in terms of vector spaces or sets or anything. We're really interested in how the morphisms combine with one another. So from that point of view, stab and spec look extremely similar. If we neglect the internal structure of the systems and the morphisms, then basically we've got, well, these objects here, and our morphisms are the closure under composition, monoidal composition, and the dagger functor of, well, a whole bunch of morphisms going from Q to Q, which form the group S4, and basically an observable structure. So we know how these combine together. That's just by definition of an observable structure. And we certainly know how these combine together because they form the group S4. So it almost starts to look like they're the same category. Any distinction between them must come from the way that the group interacts with the observable structure. And that is, in fact, the case. In fact, we can pin it down a bit more clearly than that. In fact, the phase group of the two theories is different. So, if we think about the qubit object in stab, as I said, if we pick one of the observable structures on stab, on the qubit object, let's say the one which copies these two, so these are the eigenstates, and we've got 4 unbiased states there. And so our phase group is a 4-element abelian group. And in this case, in fact, stab is the cyclic group Z4. Similarly, in the case of spec, again, if we pick an observable structure, the one which copies that and that, then these four are the unbiased states. And again, we have a 4-element phase group. It's abelian again, but I guess crucially, in this case, we have the other 4-element abelian group, the Klein group, Z2 plus Z2. Now, there's a sort of clear mathematical way of distinguishing the two theories. It's also quite important from the point of view of their physical features, in as much as this difference is key to the fact that this is a non-local theory, whereas this has a local hidden variable interpretation. And this comes about because, as I just said, these correlation triples are closely related to the phase group, and it's correlation triples of this sort which are the sort of key ingredient in probably the sort of neatest hidden variable no-go theorem in quantum mechanics. This is the, I think, fairly well-known argument, I think originally by David Mermin, which I'll just outline very briefly. Bit of a grand title for this slide. We've got 3 qubits. We're in full quantum mechanics here. We've got 3 qubits here, and they're in a GHZ state. Okay. Now, suppose we measure Pauli X on each of these. Then we find, when we do the maths, that various sort of triples of outcomes are allowed, but some are not. Some are forbidden. In particular, you need an odd number of +1s. Whereas if I measure, for example, X on this one and Y on that one and Y on that one, then I get the opposite sort of parity in my allowed triples. So in terms of the sort of abstract stuff that I've just been talking about, these are like our correlation triples. And which ones are actually permitted basically comes down to the fact that, sorry, I should backtrack a little bit. The fact that you have this parity for this type of measurement and the opposite parity for these allows Mermin to sort of derive a contradiction. If I tried to actually assign values of X and Y to each of these, which were independent of one another and didn't change upon measurement, then I'd find that there was no way I could do that without sort of infringing these parity restrictions. Now, these sort of correlations in measurements on the GHZ state stem from the fact that the phase group of stab is Z4. If I instead have a GHZ structure deriving from an observable structure with phase group Z2 times Z2, well, I can figure out what sort of correlation triples arise in that case. And in that case, the parity of these measurements changes, and they become the same as these, and you can no longer derive that contradiction and rule out hidden variables. So, I guess, where's your cheat sheet one? Sort of to sum up, we have identified this sort of piece of structure which, in this case at least, sort of endows stab with non-locality and doesn't do the same for spec. How long have I got? 2 more minutes? 2 minutes? Alright, shall I try this? No one likes to talk to finish early, right?
I'm going to wait.
Okay. Right, both spec and stab, they're both kind of similar.